All right, so we discussed about the linear motion measurement and the various principles or various instruments that can be used in the measurement of linear, let's say, displacements. We would discuss about the rotary one today, the rotary motion measurements. Now we would be focusing, or we'll be discussing a little bit in detail about the resolver, say the synchro and the gyroscopes. All right, so this is obviously about the displacement, and in the velocity one we will also discuss something called as rate gyroscopes, maybe about tachometer, and maybe about optical gyroscopes. So this is for the velocity, this is for the, say, position. All right, so this is very important. Obviously we know the significance of measurements by itself, but the at certain times we can even think of the the rotary motion. We could use even for linear measurements also, or linear motion measurements, where we convert the linear motion into the rotary motion. We can use some the rack and pinion type arrangement, or any such arrangements whereby the linear motion which we want to measure can be converted to rotary motion, and then that rotary motion, using these transducers, we can actually measure that rotary motion and correlate that with the linear motion. Though we do have several options available for rotary motion other than the resolver, synchro, and the gyroscopes. We have a number of such displacement transducers. We can list them first here. So the rotational displacement can be measured using the we do have something called a circular. We'll not talk about these things here. Circular and helical potentiometers. The pots, that we popularly call them as pots. So we do have the potentiometers in the form of pots that we use in the mechatronics, or you can say in all such applications. So I hope you are aware. Then we have a counterpart, or you can say another one similar to LVDT. We have RVDTs, where we refer to them as rotational differential transformers. Then we have the popular incremental shaft encoders. These are the optical encoders that we commonly use in the rotational, you can say, displacement measurements. These are very popularly used and very simple, I would say. Then we have coded disc, or we also refer to them as then we have the resolver, the synchro, the induction potentiometer. These are based on the principle of the inductor. So also, if we I don't want to discuss it, but it's like you have something like LVDT. You also have LVITs, linearly variable induction kind of transformers. So we do have something called as LVIT. You can maybe check it out yourself if you're interested. LVITs. And then we have the gyroscope, rotary induction, to syn. We have the gyroscopes. So we are going to discuss about these three here for the measurement of the rotational motion. Now, maybe before going in little detail, so obviously this is based on simple change in the resistance, the circular and the helical potentiometers. So it's a helical kind of an arrangement where we obviously move the tap as per the rotation of the frame that it, or the body to which it is attached to, and accordingly it varies the length of the coil, and obviously the change the resistance, and accordingly it obviously divides the voltage. We can correlate that to the position of the object that is rotating. And similar to LVDTs, we have rotational differential transformers where we, where there is, rather than linear motion, there is a rotary motion, but the concept is same. We have incremental shaft encoders, which are nothing but the optical encoders, where we do make use of I can say the photo transistors, and then we do make use of some slits through which the light passes, and accordingly, if the light passes, we have a transistor that gets biased, and accordingly you have a high and a low signal. So you get a high and low kind of signal, a square, or you can say type of a signal, whereby you can actually measure the rise and the fall and all those things, with which you can actually correlate that to the motion, you can say the position and also the direction of the rotational motion. Obviously we have some gray encoders, or you can say binary encoders, where we have which are actually called as absolute encoders, because they can give you the absolute position of the shaft also, rather than these incremental ones where you do not get the absolute one. If you just reset the the measuring system, you may get the position as 000, because it does something called as incremental measurements. So the position where you are actually reach actually has to be first noted down, then you can actually kind of correlate that to the actual position. But in the absolute ones, you do have the absolute kind of the motion that the position that can be measured with the absolute encoders, where we do have some gray and you can say some markings on the disk, so which correspond to the high or low, and accordingly you have some pattern. It could be a four say bit, or it could be 8-bit coded disk encoders also. Then we have resolvers and synchro. They are also more electrical in nature, I would say. They are more electrical in nature rather than maybe electronic in the incremental shaft ones. But they are also very popular, and they have been used particularly in defense, or you can say in the aircrafts, in the submarines, and mostly in the defense. It has been used over the over a long period now, but obviously they are also being improved upon. Maybe we need to know the principle how they actually work. Then we have something that works on the principle of change in inductance. We have induction potentiometers and rotary inductor sins, and then we have gyroscopes. So gyroscopes are generally mechanical, but we do have something called as optical gyroscopes that I have put up here. So which have come into the measurement and the instrumentation I would say industry. So we need to know how they basically what is the principle of their working. So now let's talk about the resolver. So basically it works on against the similar principle to that of the LVDT. So let's try to understand the basic principle. So we know that if a current carrying conductor a current carrying conductor actually has a magnetic field associated with it, all right, or if we wound a coil in this way, we do get a concentrated magnetic field, which is in the form of flux lines, all right. Now if we place another coil near to it, and then have a core also in between the two coils, these two coils could be concentric, they could be like this. So that we do understand that by the principle of mutual induction, we have an induced EMF will be generated in this coil, and it will also have a voltage or a potential developed across its ends. Now, obviously, this depends on various factors like the core, the material of the core, the winding, the type, the ratio and other things. So we have something called as transformation ratio. So ideally, it can be one, but generally it is not one. There are different types of losses that are associated with it. But this is the basic principle. And what happens if we have already seen LVDT also. So similar to that, if we have a coil, now let's put it in this way. So we know that if this is the input, let's say generally in AC signal in this case, so we have an output that we can tap from here. Now we do understand that what happens is if we allow this to move, that means if we allow this part, that is the secondary part, this is the primary, this is the secondary, if we allow the secondary part to rotate, let's say about this axis, so what happens is if we consider this as the angle between the two, let's say, windings to be 0, and let's assume some angle called as 90, and let's take 180. Let's not take the angles in between, just to make it clearer. And then we have 270, then we have 360. So 90, 90, 180, 270 and 360. Now in this configuration in which it's in 0, let's say configuration or it's aligned to this primary one. So we if we have the input, let's say as some sinusoidal signal and some AC with some amplitude and then some frequency, so we would see the output again in the similar form. Let's assume the amplitude is same because we assume the transformation ratio or the transform ratio is 1. So in that case, let's see, this is all an assumption. So we can see that there is no distortion of the signal. There is the phase is this is in phase with the primary also. We are able to induce EMF as per the input. So now if we rotate this by 90 degrees, so there is very least, you can say the least amount of flux lines that can actually let's say kind of mix with this, and then the mutual induction obviously principle would reduce this to almost zero output. Now similarly, if we rotate it to 180 degrees now, all right, so this means this is going upside down. So we do have a same signal, but it will be now phase shifted. All right, and similar to the 270 position, which is similar to 90 position in the reversal, we have zero output. And for the 361, it goes back to almost 0. So we have the same output to 0. So we know that by, so we understand with this the fact that if we rotate the secondary with respect to primary, we're able to actually tinker, or we're able to actually change the amplitude and also the phase of the secondary signal. So this is the basic principle behind, let's say, the resolvers and the synchros. The resolvers and synchros are almost similar. We'll just see the difference, but this is the basic principle that you do have a transformation, sorry, the transformer action. That is the mutual induction concept is here, but because we are able to rotate this and we are able to measure this, so this concept is utilized in the position measurement. So how does it basically look like? The resolver looks like this. So you have we do have some two components with this. We have a stator and a rotor. So resolvers are like, you can say, AC motors, similar to AC motors. Alright, so you have a stator and a rotor. Stator is the static part, the rotor is the one that rotates. So the coil configuration is something like this. So this is one coil, let's say, wound on the stator, and another coil is something like this. So this is, you can say, stator winding 1, this is stator winding 2. Alright, then the rotor is in obviously at the, I can say, at the middle of the whole assembly, and it is obviously positioned in such a way that it makes some let's say orientation, that it rotates with this. So it is wound, the coil is wound on the rotor in such a way that I'll just mark one of the positions. Something like this. So this is your rotor winding. Alright, so let's say this makes some angle with this stator theta, and obviously with this it may make some 90 minus theta. So The the main difference between the resolver and the stator, sorry, the resolver and the synchro is, in the synchro you have three secondary windings, which is SW1, can say SW2 and SW3, each at 120 degrees to each other. And in the resolver you just have two windings, but both of them are kept at 90 degrees. So you, in this case, if you look from the figure, you see, it seems that the winding, they are just two windings. It seems, they are just wound on the some of the axis, but it's not like this exactly. There could be there could be a lot of winding that comes in place. Let's say it's not just the way it looks like. Maybe you can check from the internet the actual photograph of the inner windings of this type of let's say instruments. But by line diagram, or you can say typically or logically, conceptually, it's like this. You have two coils which are at 90 degrees to each other, which are the stator ones, which are static in nature, which are connected to the outer assembly. And then you have the rotating part, which is the rotor, which is actually connected to the object whose position is to be measured. Now what happens is, you have different explanations for this. One of the explanation is that you do have another winding which is again connected to the stator. So stator can have three windings. All right, so the first one is the reference signal, and then second one is, we call this SW1, or this is also called as the, can say, sine winding. You have SW2, it can be also called as cosine windings. All right, so you have three, and then you have the rotor, which has just one winding. Obviously it can again have two kind of windings to increase the resolution and other thing, but let's understand this from this concept. So what happens is, you have in the stator you have a reference signal. So you do apply an alternating current, let's say through this, the first one, you do apply an alternating current, let's say some Vs sine of omega t, some alternating current through this, you can say voltage through the stator reference signal. And again, because of because of the rotor being at the inner part, the rotor and stator will have, again by mutual induction, there will be a voltage that will be induced in the rotor winding. So let's say this causes a, we may refer to this, let's say S to be the stator, or we call it as V only. And maybe in the rotor, if we have the same transformation ratio, assuming it to be 1, otherwise it's not like that, we have a factor called K, which is the transformation ratio factor, which depends on many things like winding, the type of coil, the type of core, the packing fractions and other things. So let's assume that to be unity. So the voltage induced in the rotor, suppose, would be, let's say, same, for example, in this case. All right. Now what happens in this, the principle is that the voltage that is induced in the rotor now will be induced again back into the SW1 and SW2. All right. So the design is formed in such a way that the supply or the reference signal is not able to induce in these two, but it can induce to the rotor one, and when the rotor is moving, it can induce back into the secondary ones, SW1 and SW2, in these two. And if you see the configuration as we see in the figure, so if the rotor is, let's say let's say this theta is 90 degrees, so we can see that there is a proper alignment between the two SW2 and rotor windings. So in that case, we will have the signal, or you can say the induced EMF in this case, or the voltage would be something like this, that we have seen, something like this, for example. Or let's say if theta is, let's say in this case 0 degrees, for example. So in the 0 degrees case, you have SW1 having something like this as the output. All right. So and when it reaches to 90 degrees, SW1 will have output equal to 0, because that is now let's say aligned 90 degrees to this coil configuration. Now, why do we use 2? Because we could just use 1, and that could be enough, because we could measure singles, something like this. But because we do have another one, let's say SW2 in this case, we try to increase something called as the resolution of this type of resolver. So we have, so it could be something like this, the output, or the SW1, if you want to write, maybe something like V sine omega t, but it would be in the form like the sine theta. Maybe V SW2 induced will be V sine omega t sine of maybe 90 minus theta. So if theta is 0, so this part goes to 0 and this part goes to sine 90 is 1. So we have something like this. So out of the two, let's say, because we are using two windings, so what we can do is we can get some. So if this is the reference signal, for example, if this is the reference signal, then we have, let's say, output from SW1 and output from SW2. So output from SW1, let's say at 0 degrees. So at 0 degrees, sine 0 is 0. So we have, let's say, output to be 0. All right. So it's all will be 0. And this SW2 will be in phase with this, so the same signal will be almost reproduced. And if we have at, let's say, 90 degrees, so if the reference signal was same, so SW1 will now be having a, will reproduce the original, let's say, reference signal if the transformation ratio obviously is same, and SW2 will have a 0 output. All right. So with this type of let's say arrangement of the system, what we can do is we can actually measure, and then obviously if it's between 0 and 90, so what will happen is between 0 and 90 you may have both output from SW1 and SW2, but obviously with a smaller amplitude. All right, for SW1 and SW2 also. So that means we can change both amplitude and phase, because in this case you have seen that the phase also will change as we go to, let's say, 180 degrees. There is a phase change from here to here, so a phase shift of around almost, I would say, 180 degrees. All right. So this, if we are able to measure the amplitude and phase of this output signal, which is in the form of SW1 and SW2, so we can measure both the amplitude and phase of both signals. So these two informations together can give us actually the displacement, or you can say rotation, and also the direction of movement of the rotating object, or you can say shaft in this case. All right. I hope this is clear. So we don't have to go much into details how this happens, but this is the basic principle. We can do some, we can go into the calculation part, but I don't think that is, the domain of this course. We cannot go so deeply into actually looking at what is the actual, value. How do we basically correlate that? But the most important thing is that this is an analog input device, analog output device or an instrument. So we get obviously signals in the form of sines and cosines, but we do have something called as RTDs, which is resolver to digital converters, that are available as an integrated circuit. So that can actually, process these signals to give us an appropriate value of, let's say, obviously position and the displacement and the direction. So maybe in the form of some voltage that we can probably take into the PC or the controller for processing this, let's say, the output from the rotation measuring instrument. They do have the measurement resolution of around, you can say, 0.1% of the full scale reading, and they are frictionless because they are similar to LVDTs and hence have longer life. All right. Then let's come to the synchro. Is there any question on this or any doubt? कोई है कि नहीं? मीटिंग में कोई नहीं है? अच्छा, कोई डाउट? ठीक है. तो सिंक्रो जो होता है, सिंक्रो सेम होता है, ये जस्ट वेरिएंट्स हैं आपस में, बट इसके अंदर थोड़ा सा डिफरेंस ये रहता है कि जैसे अगर हम इसको ऐसे इसकी डायग्राम बनाएं, हमारे पास एक सेकेंडरी वाइंडिंग यहाँ पे है, एक सेकेंडरी वाइंडिंग हमारी यहाँ पे है और एक और सेकेंडरी वाइंडिंग हमारी यहाँ पे. So we have 3 secondaries, SW1, SW2, SW3. So it's almost like they're making an angle of 120 degrees. I'm sorry for this. So they make an angle of, let's say, 120 degrees between each other. So that makes it to 360 degrees. And then you have a rotor. So a similar configuration to that of a resolver. इसमें एक फ़र्क क्या रहता है कि इसके अंदर आपका जो रिजॉल्वर है, रोटर है, सिंक्रो में हम रोटर को डायरेक्ट जो है सिग्नल देते हैं. With we do have something called as slip rings and brushes. इसे हम करते हैं मोटर्स में, slip rings and brushes. जैसे brush motors होते हैं. So we do make of brushes and slip rings to directly excite this rotor with the AC signal. एक और चीज़ आपको याद रखना है कि जनरली जैसे मैंने LVDT में भी, मुझे लगता है कहा मैंने, हाँ इसमें भी, we do not make use of 220 volts and all the things, but that will make it expensive, or we can say it would need a lot of resistance for a low current to pass through. So that would mean it would need a lot of winding and other things. There are other issues. So we generally make use of again voltage in the form of, let's say, I don't know, 12 maybe 100 volts also is also used, because this is used in ships, submarines, and where we do have obviously requirements. So we do have something like 12 to 100 volts, and a typical frequency is generally, because when you use a low voltage AC signal for a good mutual induction take place, you need to have very high frequency. A typical frequency of this type is used. Obviously, if you use a very high voltage, you may use a lesser frequency range also, but again, you do make use of low voltage AC also with a high frequency in this type of, let's say, instruments. तो रोटर वाइंडिंग के अंदर हम क्या करते हैं, डायरेक्ट सिग्नल देते हैं, रादर देन कि हम स्टेटर में ही दे दें और उससे म्यूचुअल इंडक्शन होकर रोटर में जाएगा, फिर रोटर से वापस उसमें जाएगा. तो लेकिन इसमें हम डायरेक्टली रोटर को देते हैं. वी कनेक्ट दिस, ऑब्वियसली ये तो कनेक्ट रहेगा टू द ऑब्जेक्ट विच इज रोटेटिंग, द पुल डिस्प्लेसमेंट इज टू बी मेजर्ड, but with the help of slip rings and brushes, we do make AC signal to pass through this. And then again, with the same transformation action, or sorry, the transformer action, you do have the mutual inductance as per the angle between the rotor and the stator coils that we have connected to the stator. We would have the output. So in this case, typically, if this is the input signal, you can say, to the rotor, okay, then we do see something like, we can maybe write it down just for our understanding. So we sine omega t to the sine of, it's a beta or whatever, theta, in this case you can write theta. So v2 is v sine omega t sine of theta plus 2 pi by 3, which is equal to 120 degrees. v3 is equal to v sine omega t sine of theta minus 2 pi by 3, or you can maybe add more than this to make it almost equal to 240 degrees. So minus 2 pi by 3 is same as plus 4 pi by 3. All right. So this is how we can see the 3 signal outputs. So we can tap them generally using, tap them on oscilloscope, or we do again have similar converters which convert them to a appropriate digital outputs. So in this case again we can see ये जो थीटा है और साइन थीटा पाई बाई 2 और साइन थीटा माइनस 2 पाई बाई 3, ये तीनों चीज़ें बेसिकली they are not time dependent. All right. So but this part is time dependent. So this is connected to the obviously the input signal. जो input signal आ रही है हमारी रोटर में, वही सिग्नल यहाँ पर having almost the same frequency. ठीक है, तो frequency is not changing. But what is happening if this V is remaining same? If we assume the ideal case where this doesn't change, so then V is same, V is replicated, but in that case V will be multiplied by sine of V theta, where theta sin theta can change from obviously -1 to +1. So which means and in between the values like 0.1, 0.2, 0.3 up to +1 and from to the left up to -1. So accordingly this V also will change. So the amplitude will also change. So at a particular position of let's say theta we can measure V1, V2 and V3. उसका अलग अलग वैल्यूज होगा. तो उसी वैल्यूज के हिसाब से उनका एक RMS वैल्यू हम निकाल सकते हैं, उनका एम्पलीट्यूड भी निकाल सकते हैं और तीनों का फेज भी निकाल सकते हैं. इन दोनों को मेजर करके इन तीन जो है टैपिंग से वी कैन एक्चुअली रिजल्ट इनटू सम डिस्प्लेसमेंट वैल्यूज एंड आल्सो द डायरेक्शन. ठीक है. इनकी एडवांटेज ये है कि जनरली हार्श एनवायरनमेंट्स में यूज़ होते हैं. फॉर एग्जांपल जिसको हम कहते हैं एरोस्पेस, नेविगेशन में, या आपकी डिफेंस अगेन हार्श एनवायरनमेंट, डिफेंस, या जनरली आप इसको मिलिट्री भी कहते हैं. मिलिट्री एप्लीकेशन में काफ़ी यूज़ हुआ है. तो आई हैव सम आल्सो गॉन थ्रू सम डॉक्यूमेंट्स फ्रॉम यूएस डायनेमिक्स. देयर इज ए कंपनी यूएस डायनेमिक्स जिसके अंदर ये काफ़ी मिलिट्री एप्लीकेशंस के लिए बहुत ही ना पॉपुलरली यूज होता था दैन दी एनकोडर्स एंड अदर थिंग्स व्हिच मे रियली फेल because of the extreme conditions and let's say there are shocks due to the ammunitions and other things, or there are vibrations that are generally prevalent in those conditions, or maybe in some industries also. And this is also used in robotics and maybe other applications. These may be obviously expensive than the optical ones. सॉरी ऑप्टिकल एनकोडर्स. इसमें हमारे पास व्हील होता है. ठीक है. इससे तो हो सकता है एक्सपेंसिव ही होए, तो लेकिन जब हमारी जो ऐसी एप्लीकेशंस होती हैं जहाँ पर हमारे ये ऑप्टिकल एनकोडर से ऐसी चीज़ें जो है दे मे नॉट रियली वर्क वेल, सो वी हैव टू एक्चुअली गो फॉर दीज टाइप ऑफ सिस्टम्स. ठीक है. सो दे आर ऑल्सो टॉलरेंट टू high temperatures, humidity, और जो आपके shock और vibration. It's also used in the machine tool for axis measurement. मेरे पास एक वीडियो था, मैं उसको प्ले करता हूँ अभी. इसको कैसे क्लिक करना है. So we have rotary ones. You may not be able to hear the audio. ऑडियो आपको हो सकता आया नहीं, लेकिन आप इसको देखें. सो दिस इज a CNC machine. So this is the motor, servo motor, that is driving the axis. So this is where the resolver actually is used. This is the resolver. So you can maybe look for this video if you are interested. So this is the one of the applications that we generally make use of resolvers and synchros. Alright, so the last part for today is gyroscopes. Can I hear from any of you about gyroscopes? Can you tell me something about gyroscopes? हाँ जी, आप में से कोई एक बताएं थोड़ा सा. I'm not evaluating you on that. सुहेब खान, सुबैर आलम, अजय कुमार, कोई आप में से बताएं. वो तो यूज है इसका, मैं इसका प्रिंसिपल पूछ रहा हूँ. वो तो फिर से एप्लीकेशन बता रहा है, मैं प्रिंसिपल की बात कर रहा हूँ. प्रिंसिपल जायरोस्कोप किसे कहते हैं? हाँ जी, खावर. जायरोस्कोपिक इफेक्ट आपने पढ़ा है अच्छे से? मतलब अच्छे से पढ़ा है, समझा है, कि अभी उसमें कुछ कंफ्यूजन है? नहीं, इक्वेशंस की बात नहीं, मैं जस्ट प्रिंसिपल की बात कर रहा हूँ कि मतलब व्हाई डज ए जायरोस्कोप प्रोसेस, बोल सकते हो? प्रिसिशन पता है ना? व्हाई डज इट प्रिसेस, मतलब जायरोस्कोप को हम वेरी गुड। चलो बेसिकली जो जब भी कोई रोटेटिंग बॉडी होती है, ये जैसे लीनियर मोशन में भी है, ये जैसे कोई बॉडी तेज जा रही है किसी डायरेक्शन में, ठीक है, तो उस डायरेक्शन में अगर वो तेज जा रही है, अगर उसको आप किसी डायरेक्शन में चेंज करना चाहेंगे, सो विल इट बी इजी और इट विल बी डिफिकल्ट? थोड़ा कोई, हाँ है ना, बिकॉज यू आर ट्राइंग टू चेंज इट्स मोमेंटम, है ना, वहाँ पर तो लीनियर मोमेंटम है। सो टू चेंज दैट लीनियर मोमेंटम ऑब्वियसली यू रिक्वायर सम फोर्स। So, इसी तरह यहाँ पर जो है बॉडी रोटेट जब करती है, इसमें भी एक अजीब सा फिनोमिनन होता है, क्योंकि इसमें क्या होता है, अब फ़र्क रहता है इसमें। जैसे लीनियर मोशन होती है उसमें तो सिंपल होता है, जिस डायरेक्शन में आप मूव करना चाहें उस डायरेक्शन में या उससे थोड़ा सा टिल्ट करके मूव करेंगे। रोटरी रोटेटिंग बॉडीज में थोड़ा सा प्रिंसिपल डिफरेंट, यानी थोड़ा सा यानी नॉन इंट्यूटिव होता है, जैसे हमें जो दिखना चाहिए वो होता नहीं है। तो वो खुसूसन हमें डायरेक्ट जो जायरोस्कोपिक जो है इंस्ट्रूमेंट से इसमें ये चीज़ दिखती है। So basically होता क्या है, when there is a body which is rotating on its axis, for example let me draw it here। जुबैर अभी क्लास है अभी उनकी, अनीफ सर की, थोड़ा वेट कर सकते हैं कि नहीं? अच्छा, देखो ध्यान से सुनिए, बहुत ही पुराना कॉन्सेप्ट है लेकिन इम्पोर्टेंट है, अगर समझ में नहीं आएगा तो ये बड़ा वो रहता है। लेकिन ये है कि इसमें थोड़ा सा आपको और भी कुछ हो सकता है, ट्यूटोरियल्स या वीडियोस मिलते हैं ऑनलाइन, उससे आदमी को थोड़ा सा एनिमेशन से क्लियर रहता है। ठीक है, तो अभी इसमें एक सेकंड इसको मैं ऑरेंज से बनाता हूँ। So I'm not discussing gyroscope actually here, but maybe we can discuss something about it because that's what leads us to the use of the gyroscope. So basically ये एक व्हील है, यहाँ पर जो ग्रीन कलर का मैंने बनाया, there's a wheel, ठीक है, it could be a disc। Generally this disc is desired in such applications to have a high moment of inertia। हाई मोमेंट ऑफ इनर्शिया मीन्स, इसका मोमेंट ऑफ इनर्शिया का अगर आपको कॉन्सेप्ट पूरा क्लियर है, मोमेंट ऑफ इनर्शिया इज अबाउट द स्प्रेड ऑफ एनी ऑब्जेक्ट अबाउट ए एक्सिस ऑफ रोटेशन, ठीक है। तो जितना दूर स्प्रेड होगा तो इतना अच्छा है। अब दूर हम ज़्यादा ले नहीं सकते, हम क्या करते हैं, थोड़ा सा बना के उसके अंदर एंड्स पे वेट बढ़ाते हैं, फॉर एग्जाम्पल एज ए डिस्क काइंड ऑफ अ थिंग। सो उसके अंदर क्या होता है, जब उसको हम रोटेट करेंगे ऑब्वियसली इसका मोमेंट ऑफ इनर्शिया है, तो वी कैन हैव ए वेरी हाई एंगुलर मोमेंटम। सो इसका एंगुलर मोमेंटम जब ये बॉडी रोटेट करेगी कंटिन्यूसली with the use of some electric motor, or you can say with the use of some string, whatever you want to do, जब इसको रोटेट करेंगे अबाउट दिस एक्सिस, ये इसकी रोटेशन एक्सिस है, तो ये क्या होगा, इसी एक्सिस के अबाउट इसका एंगुलर मोमेंटम होगा, बिकॉज ओमेगा इसी के अबाउट है, ठीक है। तो द वेक्टर ओमेगा इज अबाउट दिस थिंग, सो द एंगुलर मोमेंटम विल बी अबाउट दिस थिंग। दैट मीन्स एनी अटेम्प्ट टू चेंज इट्स एंगुलर मोमेंटम, you can say, or angular momentum, or you can say angular momentum of the rotation axis, it will be it will actually try to resist that। So any attempt to change its angular momentum, it will try to resist that। So क्या होता है, अब बेसिकली जो हम जायरोस्कोप्स देखते हैं एज टॉयज और जायरोस्कोप्स इन द लैब्स, तो वहाँ पर तो बैलेंस करके होता है, लेकिन एज ए टॉयज इफ यू सी जायरोस्कोप, सो देयर इज ए ऑब्वियसली एन इफेक्ट, और कैन से a gravitational force that always acts on this this spinning top। So it could be something like this, जैसे यहाँ पर हमारा एक स्पिनिंग टॉप होता है जो स्पिन करते रहते हैं अपनी एक्सिस पे, तो उसको अगर हम ग्राउंड के ऊपर घुमाते रहेंगे स्पिनिंग टॉप को, तो ये तो घूमेगा बहुत तेज, लेकिन बिकॉज ऑफ फ्रिक्शन, बिकॉज ऑफ एयर ड्रैग, और बिकॉज ऑफ द इंटरेक्शन बिटवीन दीज टू ग्राउंड एंड दिस, व्हाट विल हैपन, दिस विल ट्राई टू, दैट इज अ नॉन कंजर्वेटिव फोर्स ऑब्वियसली। तो उस वजह से क्या होगा, इसकी स्पीड रिड्यूस हो सकती है। और अगर इस दौरान हम ऐसा एक अरेंजमेंट बनाएं कि इसको हम होल्ड करें, इस जायरोस्कोप को जिम्बल एक्सिस पे, जैसे ये एक्सिस एक है, इसको होल्ड किया हमने, और उसको फिर खुद से होल्ड किया, और इसको खुद होल्ड किया, तो हमारे पास 3 एक्सिस हो गई, एक, लेट्स से 1 2 and 3 axis। Obviously these are the corresponding to 3 rotations of any object which can be possible in this space। तो एक तो इसकी स्पिन एक्सिस हो गई, और इसकी ये वाली एक्सिस, और ये वाली, जैसे हॉरिजॉन्टल और वर्टिकल फॉर एग्जाम्पल। तो अब क्या होता है, जैसे जायरोस्कोप के अंदर जैसे ये इसके अबाउट रोटेट कर रहा है, तो इसके अबाउट इसका एंगुलर मोमेंटम है, तो अगर हम कोई फोर्स यहाँ पे लगाएंगे, इन दिस केस अगेन बिकॉज ऑफ ग्रेविटी दिस विल ट्राई टू एक्सर्ट सम फोर्स F, एंड देयर इज सम डिस्टेंस फ्रॉम द एक्सिस ऑफ रोटेशन, सो दिस विल कॉज a torque about this point, let's say in this direction। तो जब टॉर्क इस डायरेक्शन में आएगी, इसके ये नीचे इसको करने की कोशिश करेगा, गिराने की कोशिश करेगा, विच इज इंट्यूटिव, यानी जो होना चाहिए, लेकिन होता क्या है, जायरोस्कोप प्रिसेसेस। इन दिस केस ये थोड़ा सा टिल्ट हो सकता है और फिर इसके बाद ये प्रिसेस करता है अबाउट अनदर एक्सिस. Gyroscope presses is about some axis like this. So if you see in some video, you'll be able to see clearly. तो gyroscope presses जो है ये spinning axis है, ये precess axis नहीं है. Precession about another axis हो जाता है. Gyroscope थोड़ा tilt हो सकता है इस केस में और फिर मूव कर सकता है. और इस केस में जहाँ पर हमने gimbal axis यूज़ की है, जैसे 1-2 एक्सिस हमने यूज़ की है, इसके अंदर हम क्लियरली प्रिसेशन दे सकते हैं. जैसे ये मूव करेगा और हम इसको रोटेट करेंगे अबाउट 1 एक्सिस, तो ये अबाउट 2 एक्सिस हो सकता है प्रिसेस करें. रादर देन रोटेटिंग अबाउट द 1 एक्सिस, it will precess about the axis 2. So this is the gyroscopic effect. This is non-intuitive, but this is well explained because the torque is proportional to the change of angular momentum. तो angular momentum इसको direction of torque जो होगी उसी direction में change करना है, इसी वजह से different direction में move करती है. इसको और explain अगर आप चाहें तो मैं किसी दिन कर सकता हूँ, वरना इसके काफ़ी videos भी available हैं जिसको आप देख सकते हैं, जिससे आपको clear हो जाएगा. Now in this case, in the instruments, gyroscopes as an instruments, obviously we can connect this to the frame. जैसे हमने यहाँ पर एक फ्रेम या कोई ऑब्जेक्ट है, इसको कनेक्ट किया है, यहाँ पे ये ऑब्जेक्ट अब रोटेट कर रहा है, तो यहाँ पर हम कोई ऐसा अरेंजमेंट करते हैं कि इसके साथ हम कोई मोटर लगा सकते हैं, इलेक्ट्रिक मोटर लगा सकते हैं. इसी को हम ना जैसे इट कैन एक्ट एज अ रोटर ऑफ ए मोटर एंड देन वी कैन हैव अ स्टेटर आल्सो, और इट कैन बी डायरेक्टली कपल्ड टू दी डीसी मोटर एंड एसी व्हाटएवर यू वांट टू डू. सो इट रोटेट्स इट कंटिन्यूअसली एट सम रिक्वायर्ड आरपीएम. ठीक है, तो जितना हम बढ़ाएंगे ऑब्वियसली उतना एंगुलर मोमेंटम बढ़ेगा और उतना अच्छा है. तो उस वजह से क्या होगा, तो जैसे ही बॉडी ये वाली जो यहाँ पर कनेक्टेड है विद दी शेडेड लाइंस, इफ इट मूव्स इन सम डायरेक्शन, लेट्स से ट्राइज टू चेंज दिस एक्सिस, so because of the gyroscopic effect, so because we have connected them with gimbals, so this will rotate about some other axis, and obviously it can rotate about this axis and this axis. Because this axis we are not interested, this is the spinning axis, so we can mount some, let's say some we can have some, let's say secondary instruments. In this case again ये भी secondary type का बन जाएगा. उसके अंदर में क्या हम encoder कुछ यहाँ लगा सकते हैं 2 और 1 पे, तो जो हमें बताएगा कितना मूव किया इसमें. ठीक है, accordingly we can determine the rotation of this object, how much it has actually rotated. ठीक है, so we do have a gyro wheel, we have the these are the two outputs, output 1 and output 2. ठीक है, this is the spinning axis and this is the gyro wheel. These are the gimbal mechanisms, and these are obviously attached with bearings on the housing. ये भी suppose bearing है, ये भी bearing है. ठीक है, तो प्रॉब्लम क्या होती है जायरोस्कोप्स में, they are generally called as inertial used generally or properly referred to as inertial navigation system because they are on the principle of inertia. You can say moment of inertia, so that's why they are typically called as inertial navigation systems. इनका ये रहता है जनरल, इसको हम दो में डिवाइड करते हैं जनरली. फ्री जायरोस्कोप्स, ये वाला फ्री है, फ्री जायरो, दिस इज फ्री अबाउट ऑल 3 एक्सिस. देन वी हैव दी एक सेकंड, इसका नाम है रेट इंटीग्रेटिंग जायरोस. सॉरी, रेट इंटीग्रेटिंग जायरोस. ठीक है, एक तो फ्री जायरोस है, एक रेट इंटीग्रेटिंग जायरोस है, इसका बताऊंगा मैं. तो फ्री जायरो ये वाले हैं जिसमें अब दोनों एक्सिस हमारे आउटपुट एक्सिस एग्जिस्ट कर सकते हैं और हमारे पास स्पिन एक्सिस है. तो इनके अंदर हमारा 10 डिग्रीज को ये इजीली मेजर कर सकते हैं. आप कह सकते हैं कि दिस इज वेरी स्मॉल, बट व्हाट हैपेंस एक्चुअली these types of gyros are not much used, rather than we have rate integrating gyros which are used. So in this case 10 degree भी जो है बहुत इनफ है, जो भी हम यूज़ करते हैं कंट्रोल सिस्टम के लिए. वी हैव कंट्रोलिंग बाय जायरोस बिकॉज जब भी हमारी जो एक्चुअल पोजीशन जो हमें मीट करनी है उससे अगर ये ड्रिफ्ट भी करेगा, जनरली कंट्रोल ड्रिफ्ट हमारा 10 डिग्रीज तक भी जाता नहीं है, 2 डिग्रीज 3 डिग्रीज तक जाता है. उसके बाद हम कंट्रोल एक्शन और प्रॉपर कंट्रोल एक्शन लगाते हैं उस सिस्टम पे और वो वापस आ जाता है अपने रेफरेंस पे. तो उस केस में हमारे लिए ये काम आ जाता है. सो इट्स एनफ फॉर अस. बट फॉर 3-dimensional रोटेशन मोशन ऑफ लेट्स से एन एयरक्राफ्ट, so we may have to use 2 free gyros because ये हमें सिर्फ 2 डायरेक्शन में रोटेशन कितना हुआ वो दे सकता है. so we make use of 2 free gyros which gives us let's say 4, which we can superimpose and we can correlate back to 3 axis rotational motion measurement. ठीक है, तो can also say that they measure the absolute position, or you can say rotation, about the perpendicular axis of the body to which the frame is attached. इसमें methods of driving the wheel में हमारे पास एक तो इलेक्ट्रिकल है, इसमें मोटर यूज़ कर सकते हैं या डायरेक्ट इसी को मोटर बना सकते हैं एज ए रोटर, और एक स्टेटर लगा सकते हैं, और वी जनरली यूज मेक यूज सम फिक्स्ड vanes on the rotor which can be driven by some air jet. This is also used if you go through some of the websites or the YouTube lecture, some YouTube animations. There are some fixed vane type rotors also. जैसे एयरक्राफ्ट में हमारे पास कंप्रेस्ड एयर या इस तरह का एयर रहता है ऑलरेडी, तो हम वैसे भी उसको डाइवर्ट कर सकते हैं उस एयर को फिक्स्ड वेन ऑफ रोटर में, इलेक्ट्रिसिटी बचाने के लिए हम वैसा भी कर सकते हैं टू ड्राइव दैट spinning wheel, so that we can make use of this as an instrument. So we do have something called as drift. जैसे हमने पढ़ा था zero drift या sensitivity drift. What happens is because of the friction, which we cannot generally avoid, we may make things very quite fine, but still there is some amount of friction in the bearings and maybe in the whole connection between the obviously the gimbals and the frames. We have bearings, so we do have some sort of friction there. Because of this thing, we have some phenomenon called drift that happens there, and then it is around the drift of we generally measure, let's say 0.5 degrees per minute, which means after, let's say roughly if it's 10 degrees, then we have around some, you can say 10 minutes or something like that. After some time, let's say 10 minutes, we may have to recalibrate the gyro instrument. तो ये जनरली होता था पहले भी, काफ़ी रिकैलिब्रेशन हर 5 मिनट के बाद या 10 मिनट के बाद the pilot or the person in those circumstances would change it back to zero if he is moving in a straight path. So that thing had to be done. So that's why this is not used much, though this is again used because if it's just 10 degrees and when we can do this recalibration, this type of gyro is also used. I think we are done with it, and we then have something called as the rate integrating gyro. एक सेकंड यहाँ पर मेंशन करता हूँ. इसमें क्या करते हैं बेसिकली, इसमें this is similar to the free gyroscope, but what we do is we fix one of the axes. So let's say we don't allow it to rotate here, so this gimbal is removed, so we just connect it directly to the frame and only one axis is allowed to rotate. तो उससे क्या होता है, उससे हम प्रिसिशन को अवॉइड करते हैं, प्रिसिशन हम अलाउ करते नहीं है उसके अंदर. तो उसके अंदर ऑब्वियसली कुछ, जब प्रिसिशन नहीं होगा तो ऑब्वियसली प्रिसिशन रेजिस्ट करने के लिए कोई टॉर्क लगेगा, तो वो फ्रेम पे लगता है. लेकिन इसकी डिसएडवांटेज ये रहती है कि इसके अंदर हमें एक ही रोटेशन मिल सकती है. तो इसको मैं एक इसमें बनाता हूँ. दिस इज ऑल्सो गिवन इन द बुक्स, समथिंग लाइक दिस. इफ यू ड्रॉ इट समथिंग लाइक दिस, ये हमारे पास रोटेटिंग डिस्क है. तो हमारे पास एक जिम्बल है, बाकी इसको हम सीधे फिक्स करते हैं यहाँ पे और इसको हम फ्रेम के साथ लगाते हैं. So only one, this is not allowed to rotate, so this is obviously rotating with respect to this. This is our spin axis and this is the output axis. In this case, the other one which has been, let's say, removed can act as the input axis, because this जब ये रोटेट करेगा तो इस डायरेक्शन में ऑब्जेक्ट रोटेट करेगा, बॉडी रोटेट करेगी, इस डायरेक्शन में उसका मूवमेंट आएगा और वो मूवमेंट हम मेजर कर सकते हैं. ठीक है, तो उस वजह से वी कैन जस्ट मेजर वन रोटेशन with this type of gyro. So that means for 3 rotations which we generally desire, we will need 3 rate gyros to be in place for the measurement of 3 rotations. ठीक है। अब इसके अंदर भी थोड़ा सा स्मॉल मैथमेटिक्स है, बट आई डोंट थिंक वी नीड टू गो मच इनटू दिस, वी जस्ट नीड टू अंडरस्टैंड द कॉन्सेप्ट्स हाउ बेसिकली दिस वर्क्स। इसके अंदर एक आता है, उसको कहते हैं आजकल जो मैं पढ़ रहा था इसके बारे में, वी हैव समथिंग कॉल्ड एज रिंग टाइप जायरोस्कोप्स या ऑप्टिकल जायरोस्कोप्स। ऑप्टिकल जायरोस्कोप में एक वीडियो भेजूंगा आपको, तो उसमें हम आजकल जिसको कहते हैं मैकेनिकल जायरोस्कोप्स। ऑप्टिकल जायरोस्कोप्स में क्या होता है, उसमें हम कॉन्सेप्ट ऑफ लाइट यूज करते हैं। लाइट थ्रू लेफ्ट थ्रू लेजर एंड अलाउड टू मूव इन सम पाथ, then the moment we change the rotation of that part is rotated, so the light experiences some shift. So that shift can be measured with some instruments, and we can easily correlate that shift to the rotation of that body. So they have now probably, I would say, much replaced these type of mechanical gyroscopes also. So that's why to me as a let's say as an engineer or as a teacher, or maybe you also as a student of this course, you should know what is the trend. It's not that let's say this is all going out, but how things are replacing the things that were existing. What are the basic principles that exist, and how in instruments or in industry that you may go, let's say tomorrow, or you may like to use these things in some applications. You should know what is the current trend, what is being used. So these fiber optics, we call them FOGs, fiber optics gyroscopes, are popular these days. Maybe if I get time in the next class, I will try to show you, because that also is used in the measurement of rotational velocities. ठीक है, any questions? हाँ जी, खबर या जुबैर या बाकी जो भी आपके स्टूडेंट्स हैं, कोई है भी यहाँ की? ठीक है. Still I have myself, let's say, sometimes when we study these things, you have some doubts in the intuitive understandings of how these work. So there are some good videos that I have tried to go through. उसमें से मैंने कुछ फिल्टर किए हैं, कुछ वीडियोस वो मेरे पास हैं, तो मैं अगर आप चाहें तो उनको फॉरवर्ड करता हूँ एज ए लिंक on the Google Classroom. If you are interested, you can go through them. It may give you a better understanding. But there are sometimes some explanations which may not be correct, because जैसे YouTube पे तो कोई भी डाल देता है, कोई भी स्ट्रीम करता है, लेकिन कभी कोई वीडियो या कोई एनिमेशन जिसने काफ़ी मेहनत से किया होता है, दैट इज समटाइम्स फिनोमिनल, मतलब उससे काफ़ी आदमी सीख सकता है, और जो है जो अंडरस्टैंडिंग में आपको हाथ से या इस चीज़ से डायग्राम से नहीं दिखा सकता, विद अ गुड एनिमेशन यू मे बी एबल टू अंडरस्टैंड समथिंग्स मच बेटर. ठीक है. एंड यू मे ऑल्सो हैव टू, इट्स वेरी इंपॉर्टेंट फॉर यू एज अ स्टूडेंट टू अंडरस्टैंड दैट आपको बाद में रेफरेंस एज ए बुक उसको भी देखना पड़ेगा. ऐसा नहीं कि आप जैसे अभी आप जैसे यही रिजॉल्वर के बारे में देखेंगे एक बुक के अंदर, तो उसमें डायरेक्ट रिजॉल्वर को ही हम जो है एक्साइटेशन दे सकते हैं. ऐसा भी हो सकता है कभी रिजॉल्वर को नहीं, स्टेटर को एक्साइटेशन देके रिजॉल्वर को म्यूचुअल इंडक्शन के बाद फिर रिजॉल्वर से वापस स्टेटर, ऐसे भी देयर आर डिफरेंट वेरिएंट्स आल्सो. सो दैट यू शुड अंडरस्टैंड दैट it's not just that something that you study on YouTube, that will be actually what is there in the books, or that what is actually being followed. So both things have to be taken together. You cannot leave the actual text, the actual references that exist in the form of, let's say, good lectures or books, and also you can supplement them with some animations like this. Okay, I think that's it. If you have any doubts, otherwise we can maybe discuss. If you want to discuss about the professional web, I can just maybe quickly tell you what it's all about.